Okay, so the second part of this transition from section 5.2, talking about similar matrices, to talking about diagonalization in section 5.3. All right, so first of all, we need a definition. Okay. We say that a matrix A is diagonalizable, which often gets shortened to diagonalizable or diagonalizable, I don't know. Anyway, we say a matrix A is diagonalizable if and only if there exists a diagonal matrix that is similar to it. Who cares? Why would you want to have a matrix be diagonal or diagonalizable? Well, that all boils down to what's so great about diagonal matrices anyway. So if you have a diagonal matrix, by that, it means it's got values lambda 1, lambda 2. Yeah, I could put other letters in there, but those are its eigenvalues, aren't they? So let's just call them that. If it's got its eigenvalues on the diagonal and zeros elsewhere, you can use block multiplication defined on page 20 of section 2.4 to prove that if you take powers of D, raise them to the nth power, multiplying matrices, regular matrices, just any matrix A multiplied by itself, ugly very, very quickly, right? But for diagonal matrices, their powers are just a matrix that has the powers of its eigenvalues. So diagonal matrices have this lovely property. They have the property that they are wearing their heart on their sleeves. They're wearing their eigenvalues right on their diagonal. Very easy to find their eigenvalues. And if a matrix is diagonalizable, if it is similar to a diagonal matrix, any matrix that is so is also has this nice property that its nth iterate will be equal to, will be similar to the nth iterate of its diagonal. I think we talked about this last time, right? If you took a P, D, P inverse and multiplied by itself many times, the P hitting the P inverses would disappear and leave you with this. So for example, suppose A is similar to a diagonal matrix that has 1, 1/2, and 2 on a diagonal. Or another way of saying this is suppose A is a 3 by 3 matrix that has eigenvalues 1, 1/2, and 2. Right? Well, we're going to when we get to this next theorem, you'll see why I'm doing that. Anyway, so suppose A is diagonalizable, is just similar to such a matrix, such a diagonal matrix. Then the 100th iterate of A would be similar to the 100th iterate of D with just multiplying by B on the outside left and P inverse on the right, which, by the way, is really just a change of coordinates. We're going to get to that next week. So where D to the 100th power, look what it looks like. That's a 1 raised to the 100th power, which is just a 1. A 1/2 multiplied by itself 100 times, that's 1 over 2 to the 100th. Very small quantity. And 2 raised to the 100th would be the corner entry here on D to the 100. So notice that no matter how ugly A is, its 100th iterate is similar to this one, and therefore, since 1 here it was eigenvalue, lambda equal to 1, its eigenspace is stable, right? We talked about that, where if AX equals 1x, then X isn't perturbed by A at all, it's fixed. So we have one eigenspace that's totally fixed, the second eigenspace, after many, many hundred iterates of A, the second eigenspace, it's going to the 0 vector, right? Because ax is equal to 1, a to the 100x is equal to 1 over 2 to the 100 times x. In other words, really, really small fraction, close to 0. So that eigenspace is just disappearing, not having any influence. And this third one with lambda equal to 2, it's getting magnified. That's practically infinity, right? Infinity times whatever the third eigenvector is. So if it's diagonalizable, its dynamics become transparent or much more malleable than usual. Okay. Let's look at some examples of diagonal matrices. Excuse me, diagonalizable matrices. All right, can you read this? I think you can. For example, any diagonal matrix is diagonalizable. Why is that? Well, to be diagonalizable, you just have to have a matrix P that's invertible, such that P inverse DP is equal to the original. Well, take the identity, right? So any diagonal matrix is diagonalizable. If you just want an easy example of one, that's kind of a trivial one, right? And what's happening with my camera? Let's try that. Okay. No, I don't know what's going on there. Well, that's flopping. Okay. Another one. An example from the last video. We had a matrix A. We showed it was similar to a diagonal one there. So there's an example of a diagonalizable matrix. You could go off and find its eigenvalues and eigenspaces and notice what's interesting about those. Stop the video, do that, come back. That would probably be a really good idea. All right, so let's say you're back and you're prepped now for what we really want to talk about. The main show here is that, oh my goodness, this thing feels like it's about to fall right off. All right, now glare. Let's get rid of that glare there. All right, for the first panel, I think we're good. Right here? Yes, okay, good. So there's a big theorem, the Diagonalization Theorem. It's Theorem 5 of section 5.3. You should be able to prove both directions, okay? Any n by n matrix with n linear, oh yeah, here are both directions. I split them up into two explicit different statements. Your book phrases it as an if and only if. Any n by n matrix with n linearly independent eigenvectors, that last example, remember, is diagonalizable. The other direction is that if there is a matrix P that is invertible and a diagonal matrix D such that A is equal to P dP inverse, or that A is similar to D, then A has n linearly independent eigenvectors. Well, you could go off and make a basis with one of those, the best kind. So let's look at the proof of part A. Okay, so it starts here. So we're assuming that we have an n by n matrix that does have n linearly independent eigenvectors. We're going to show it is diagonalizable. Well, so line up its n linearly independent eigenvectors. Notice that the lambda I here do not have to be distinct. If you remember the previous video, we had a matrix with lambda equal to 2, and it had two linearly independent eigenvectors associated with that eigenspace for lambda equal to 2. So you can have both of these, say, are equal to 2, the same eigenvalue. and x1 and x2 different eigenvectors. All right, so suppose you have lined up your n linearly independent eigenvectors. Form a matrix P by taking the xi, the eigenvectors, and putting them in as columns. In the same order, put a diagonal matrix with the lambda I matching from this equation. Okay, same order, has to be same order. So first of all, you can prove that P is invertible, right? Because all its columns are linearly independent. You've got n of them. Therefore, P has to be invertible by the invertible matrix theorem. Secondly, or thirdly, recall that we had a trick that we've been using all semester. That the product of two matrices AB can be rephrased as A times the first column of B, A times the second column of B, A times the nth column of B. That guy has come in handy over and over again. Here's another time. So therefore, any matrix A, which is equal to A times I, the identity matrix, remember, can be made up of E1, E2, En, where that's the standard minimal basis, right? So any matrix A could be expressed as AE1, AE2, AEn. In other words, the ith column of A can be expressed as A times EI. All right, so we get all those tools together, then this proof goes lickety-split. And is there a glare? Maybe I got the glare in just the right place. Let's see. Can you read that? Nope, you can't read that. But now you can. Okay. All right. So we're trying to show, we're doing the first part, right? That if you have n linearly independent eigenvectors, you can show that A is similar to a diagonal matrix, right? So we have cooked up a matrix P by taking the eigenvectors of A and putting them in there. We cooked up a D by putting the eigenvalues of A along its diagonal. So P times D looks like that. And that is equal to this, right? If you take lambda 1 and multiply by E1, well, that is exactly what that first column is. Lambda 2, E2, second column, lambda n, En is the nth column. Multiplying this matrix by that, by our nice little trick that we've been using over and over again, that just gives you P times the first column, P times the second column, P times the nth column. What's going on from here to here? We're just scooting the scalar out in front of the matrix. Now what's going on from here to here? P times E1, well, that's the first column of P. Remember, we established P had columns made out of the eigenvectors, the xi. Okay, so we have lambda x1, lambda x2, lambda n xn, but that's the same thing as ax1, ax2, axn. Why is that? And this is, well, that's A times P, because P had as its columns x1, x2 through xn. So PD is equal to AP, and therefore A is equal to P dP inverse. Because remember, P, we proved it, is invertible. Yes, I'm solving for A here by multiplying both sides on the left by P inverse. So therefore A is similar to B, and that's the end. A is diagonalizable. It's similar to a diagonal matrix. So if you have n linearly independent eigenvectors, you can easily, if you already have them in hand, you can create your diagonal matrix D and your invertible matrix P out of the eigenvectors and eigenvalues. What about the other direction? All right, so proof of part B. Part B is here. Right, if there is, so you have some matrix n by n, and you also have an invertible matrix P and a diagonal matrix D such that that equation is true. Well, then you now know A has n linearly independent eigenvectors. That also comes in very handy for forming a basis out of eigenvectors, which it turns out is very desirable. All right. So putting those pieces in your mind, let's do for part B. This one here. Okay. Well, you've been handed a matrix P, right? So let's let the columns of P be called the set of Pi. I equally 1 through n columns of P by. All right. Well then, what do we have? What do you know about P? If P looks like this, P1, P2, Pn, and you're given that P is invertible. So P inverse exists, right? Well, then your matrix A being equal to P, D, P inverse, that was also given. This implies that AP is equal to PD. What do we do from here to there? Multiply both sides on the right by P. And so that's giving us that A times P1, P2 through Pn, that's that left-hand side there, is equal to P times, we already have D, a diagonal matrix. Let's just call it D11, D22. Let's call its diagonal elements. That big zero is elsewhere, right? Of course, it's going to be true that these are not only the eigenvalues of D itself, but of A. That's what we're proving. Okay, so what do we have here? So this left-hand side here is equal to the matrix with AP1, AP2, dot, 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 APN. Okay, and what does that look like? Well, that looks like P times the matrix. So D11 here multiplied by E1 is the same thing as that first column. D11 E1, D22 E2, dot, 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 DNN EN. Right? Looks familiar. Should look familiar. Similar territory, but different emphasis. Okay. And so that gives us that this matrix here, which is AP, right? This is AP, equals that. So can you see over here? So AP is equal to, oh yes, so I have P, this matrix multiplied by all this. I'm going to use the trick and write that as P D11 E1, P D22 E2, P DNN EN. Similar. We're going to bring out this constant D11 P E1, D22 P E2, DNN P that's going to give us D11. What is that? That's just the pth column, the first column of P. This is D22, P2. This is DNN, PN, the nth column of P. And so I've shown that AP is equal to this. And that gives me, that's equivalent to saying, take the ith column of this. That looks like API, right? One of those down there. API is always equal to DII PI for I equaling 1 through n. So what do we have? Therefore, the ith column of P, whatever invertible matrix that was given to us in the beginning, that worked in that relationship there, the ith column of P is an eigenvector of A. And we already had the columns of A, the PI, were linearly independent. So since P invertible, that implies this set of PI, those eigenvectors, ith column of P, that is our PI, I equaling 1 to n, is a linearly independent set. Independent set of vectors. They're eigenvectors, they form a linearly independent set, and there's n of them. And that's that.